Okay, it looks like we already have 23 attendees. That's a lot. So maybe it's time to get started. It's our great pleasure to have Professor Dustin Schroeder from Stanford University to join us today as our seminar speaker. Dusty got his bachelor degree from Bucknell University and his PhD from UT Austin. He then joined the JPL as radar system engineer before coming to Stanford as assistant professor in 2016. Dusty's research focused on ice penetrating radar and using it to study ice and water systems on both Earth and the planetary bodies. And due to his outstanding contribution to our community, Dusty received the NSF Career Award, one of the most prestigious awards for junior researchers in this country in 2018. With this, we'll welcome Dusty to give his talk titled, what is it? Titled Radar Sounding Insights from the Amundsen Sea from West Antarctica. It's all yours, Dusty.
All right, great. Thank you for having me. It's nice to see so many familiar names in the participant list, and I'm sad I can't be seeing you guys in person, but it's nice to have this opportunity to talk to you about some research and give my first seated seminar, so we'll see what that experience is like. For today, I want to talk about sort of maybe the longest lasting research thread I've had. So my group spans electrical engineering and geophysics. Some of my students build radars. Others of my students, are glaciologists who use radar. Everybody's ice and radar. And so we study all sorts of things, as said in the introduction, including icy moons. But the Amundsen Sea Embayment of West Antarctica is the first area that I studied, and many of my students continue to do work that's relevant there. And this seminar was really an opportunity to try and track that thread through, maybe offer you guys an updated mental model of what I think the current state of ice penetrating radar knowledge on that part of West Antarctica is. Okay, quick introduction, which many of you here already know. Like most glaciologists, I start my talks, with an introduction on trying to project sea level out of the next 100 years, right? And the main takeaways here are, when you look at projections like this on the FECC and this range of uncertainty, that's a large range. This affects how we build our cities and, how many people are affected and displaced. But even with this range of uncertainty from our current models, our current rate in terms of past sea level rise is not the highest the Earth has produced. And even the steepest slopes here, this dashed line, the Earth is capable, or at least was capable in the past, of much higher rates of sea level rise. And so I, like many glaciologists, are trying to understand, is the Earth currently or on track to produce some of these bigger numbers? So again, why, building towards why this talk focuses on the Amundsen Sea Embayment, again, in logic that I think will be familiar to many of you. If you want to look for glaciers that could go away quickly and can contribute to sea level rise quickly and produce some of these bigger numbers we've seen in the past, the first thing you would look for is the bottom of the ice sheet below sea level. It gives you mechanisms that could cause the ice sheet to go away more quickly. So in Greenland, we see sort of, the center of the ice sheet bed is below sea level, but not the coast. So the high topography on the edge sort of can serve as a brake for the maximum speed limit of ice flow and sea level contribution. East Antarctica has a lot of ice, right? Much of it is its bed is above sea level as well, except for some sectors down here. And then you have West Antarctica, where a lot of the bed is below sea level. So this is the reason why a lot of attention is paid to West Antarctica with this question. Now, if you were to say, okay, we want to zoom in a little more here, you might be attracted to areas where the ice is flowing quickly. So if you look at INSAR velocities, you might get attracted to this area over here, as our field was for a long time. We have really fascinating areas here, these purple areas of fast ice flow, where you have fast flowing ice right next to areas of slow flowing ice where there's no strong topographic constraint on why one's flowing quicker than another. You have this area here where we know ice was flowing quickly, but from the radio stratigraphy of the ice itself, we know it slowed down and stopped, or slowed down a lot compared to how it was flowing. But if you look at the gravity signature over there, this area, which was nicely accessible from a US base and sort of interesting in terms of these processes, it's sort of in balance. The mass loss from gravity isn't that large, certainly compared to this massive mass loss over here in this box, right? And here you have the Amundsen Sea Embayment. So these two glaciers here, Thwaites and Pine Island, are flowing quickly. They're purple in terms of the velocities, and they have large mass loss. So that's why we're going to focus on the Amundsen Sea Embayment. Now, if you want to zoom into the Amundsen Sea Embayment as well and sort of prioritize glaciers that you think could produce a lot of sea level rise, the next thing you would look at is where's the bed of the ice sheet sloping inland, right? So the reason for this is if you have a glacier flowing, it flows like a viscous fluid. So if you were to, spread a thin layer of honey on top of a table, it would flow slowly. If you were to pile up a cylinder of honey somehow for some reason and then let it go, it would flow more quickly because gravity was pressing down on it, right? So the thicker it is, the faster it would flow. So you can imagine if you have a glacier like this, it's vomiting out icebergs, gets a little thicker, right? Thicker it is, flows faster, more icebergs, thicker, faster, more icebergs, you can have a positive feedback like this. So if the bed of the ice sheet is sloping inland, that's a potential instability, potential positive feedback. And we can see these two glaciers, Pine Island and Thwaites, if you look at their beds, they both satisfy that condition. They're both sloping inland. But you can see in the case of Pine Island, if you started a retreat and you had that positive feedback, eventually you would have this high topography here that would stop it from spreading to the rest of the ice sheet. In the case of Thwaites, you can see it's landward sloping the whole way into and a retreat could spread to the rest of the West Antarctic ice sheet. This is not unique logic. There's a whole paper, How Much, How Fast, written about this. There was a whole call of joint US-UK field experiments that could only propose to study this glacier. You have all these experiments with airplanes and robots and submarines and boats. Everybody's got acronyms. There's like MELT and Tarzan and GHOST. I'm involved with the TIME project. Originally, I think the Thor project didn't have an acronym, but it felt left out. So it renamed itself. It got an acronym too. And everybody's going and everybody's studying Thwaites. And that's great. I think that's right to really focus for the logic I just laid out on trying to understand this glacier and how it's going to change. But as enthused as I am about studying Thwaites, I think there's a question of, have we zoomed in a little too far? Should we be looking at the ecosystem of Thwaites and Pine Island together, the whole Amundsen Sea sector? And are there things we can answer before all of those acronym experiments bring back their data or as they're starting to? And what I want to leave you thinking about today about this sector, right, is to think about the boundary between these glaciers, right? So you have Pine Island, Thwaites, two of the fastest changing, most mass losing glaciers in Antarctica. And all along this boundary between them, we have this area of the Bentley Trench, the eastern shear margin, the Walgreen Coast here, the southwest tributary of Pine Island, and the eastern ice shelf of Thwaites. So I want to think about potential interactions across this boundary. In terms of the types of things we want to talk about and think about along those boundaries, there are some people who study these glaciers in this region who see the main dynamic forcing thing to understand is the ocean. The ocean is moving heat, is melting the glacier is responding to that. And in some cases, the ocean is driving the bus. And in that case, in these people's mental models, often the ice is sort of like a big dumb block of ice sitting on a big dumb template of rock. And then, the ice sheet responds to the exciting dynamic ocean or atmosphere. The view I'm going to try and put forward here is to look at cases where the mental model is sort of the opposite, where the ocean is doing its thing, it's forcing, but how the ice sheet responds. We're going to think about things internal and beneath the ice sheet that could be shaping that. So questions like whether the bottom of the ice sheet is lubricated by subglacial hydrology, whether the bed is deformable sediments or bedrock, the geothermal flux of the bed, internal things like the fabric, the ice fabric of the ice sheet itself, and even surface processes like melt on the surface and permeability of the surface of the ice sheet. And when we do look at the ocean, going beyond simply the question of warmth deposited on the edge of the ocean and questions like how much water is, say, getting under the edge of the ice sheet. So these subsurface conditions we're really going to focus on. The other thing, since we're focusing on these subsurface conditions, and because, I love it more than most things in life, we're going to focus on ice penetrating radar. And so in this case, we're going to talk about radar sounding. So if you're familiar with perhaps surface radar that gives you velocities and instars, that's sideways looking radar that makes a 2D image. We're talking about radar sounding where the pulses are down vertically through the ice sheet and they come back, right? So it makes records that look like this, maybe closer to active seismic records than say surface images of the radar. So your pulse goes down from your airplane, comes back up. You collect it along profiles like this. So this is a map of the data collected over decades from many different radar systems. Gridding those up is how we get maps of the bottom of the ice sheet like this. And an individual profile looks like this. And you can see this is going through kilometers of ice, which is amazing. If you've had any experience with ground penetrating radar going through things that are not ice, it's often hard to go through meters or tens of meters, and you're going through kilometers of ice. This is like 500 kilometers along. So we're seeing this is the shape of the whole ice sheet itself. You can see areas where there's beds, you can see the layers, you can see the edge where the ocean is. And a lot of glaciology has used ice penetrating radar because this is so powerful. Lets us see the topography, lets us see the structure of the ice sheet. There's a lot that's visually there for you that you don't have to sort of quantitatively analyze the information in the radar data itself. My group is dedicated to doing the opposite. We're doing that as well as analyzing the echoes themselves. And so the mental model here for the sort of information we're going to be talking about is if you get a reflection from the bottom of the ice sheet, and you look at how bright that reflection is. So for example, this is a subglacial lake. So you have mountains here, mountains there, and that's a lake. The reflection from the lake is stronger at that interface because the dielectric contrast between ice and water is strong. You can see in this table here, this is in dB, but if you have sort of frozen groundwater, frozen bed here, you have like negative 30 dB, it's 10 to the negative 3, and then you have water here, 10 to the negative 2. So that's like 1,000 times brighter. So on the one hand, compared to a lot of geophysical signals, a nice, bright, 1,000 times brighter reflection is a big signal to look for. So that's a reason to be optimistic that we could really look at conditions like water on the bottom of the ice sheet. Now the challenge is you're also propagating through the ice sheet itself. And you can see here, this is attenuation as a function of temperature. And the main thing to look at is this is sort of an exponential curve. The warmer it gets, the more water, again, is in the ice sheet, or it starts to thaw a little bit. It can absorb energy more. And you can see that this is in units of dB per kilometers. This is exponential units over linear distance. And so given that exponential units, and given that it's also curved, that means as you get warmer and warmer, it can absorb a lot more energy. So there's ambiguity when you get a reflection that's stronger. Is that stronger because there's more reflection off the bottom because of the contrast between water and ice? Or is that reflection stronger because the ice was colder and it absorbed less? And so this is an inherent ambiguity in any one echo, but it also gives us some richness that we can exploit to try and separate those two effects. So that should be your sort of mental model of when we're talking about this radar data, what is the sort of information we're thinking about? All right. So the first area along this boundary between Thwaites and Pine Island I want to talk about is the Bentley subglacial trench. So here's the Bentley Trench this year. Already looking at the ice flow, it looks weird, right? There's this big blob of ice that flows out of Pine Island, doesn't flow into Thwaites. If I was to draw this, I don't think I would ever think to not draw this ice flowing into Thwaites like that. I don't think I would ever think to have it go into Pine Island. Feels strange. The other thing that's strange about it is if you model the water flow, the water routing for subglacial hydrologic potential, where subglacial water would flow, that water flow into Thwaites, not Pine Island. So those are both weird. It looks weird, and the water and ice are flowing in opposite directions, or not flowing in the same direction, let's say. And one of the reasons that I think this has not been looked at as much is that if you look on the right here, there are two surveys. So the Browner survey was collected by a British Antarctic survey radar system, and the purple was collected by University of Texas radar system. And these are collected at different frequencies, different pulse lengths, different receiver gains, even though they're collected at the same time. And this area that governs, where does water flow between Pine Island and Thwaites, and what's happening on the bottom, that's right at the boundary of these surveys. So in order to answer these questions, it requires us to calibrate these two systems to each other. So I think that's one of the reasons this hadn't been looked at as much. So we went through an effort in our group to do this. And so what we what we found, one, we were very lucky that there was a repeat flight of the two systems. So even though their center frequencies were different, even though the receivers were different, we had a bang on repeat flight, and we were able to cross calibrate the systems. And we were able to, for the first time, produce a cross catchment reflectivity map, which you can see here on the right. Now, you guys, we just talked about this. Waters can be more reflective, so you can see these bright, in this case, red colors are going to be areas where you'd think it would be thawed or water, and these cool colors were areas where you'd think the bed would be frozen. And this offers us a clue for maybe why this ice is flowing into Pine Island from the Bentley Trench, is that you see there's this big area of frozen bed there at the top of Thwaites where you have slow flow. So if this is the case, if the water would be routed down here, but this area of the bed just happens to be frozen, that means that as Thwaites speeds up and as both of these glaciers evolve, that could put this whole area of ice, which currently flows into Pine Island and currently is budgeted as the catchment of Pine Island, into the catchment for Thwaites, and Thwaites could grab that, and all of a sudden its area and sea level potential would increase. So I think that's a provocative thing that comes out of this sort of nerdy cross-system calibration effort. The other thing that this effort adds is some insights into the water system itself. So by doing these calibrations, we're able to both look in to these areas where altimetry shows active lakes, and we're able to look at both the reflectivity, the corrected for reflectivity and specularity, which is how sort of mirror-like the reflection is. So you can imagine if something's reflecting like a mirror, just like if you've ever flown over Minnesota and had a small pond reflect the sunlight into your eye. If you're sitting, by a window in an airplane, even though the pond's small, it makes it more mirror-like and dominates your reflection. This gives us a window into what's happening in these lakes where they're specular, but then you have these changes in terms of the reflectivity. So that gives us a window into sort of what's perhaps happening on the bottom of these active lakes. And similarly, when we look at the transition from these high specular regions to less specular downstream, which was an observational study we had done in the past, you can see that it corresponds to some of the modeling work that's being done now in terms of areas where you have water covering more of the bed upstream in Thwaites and going into more concentrated flow paths downstream. So there you go. So making these two corrections between these two radar systems allows us to look at the whole catchment, gives us an idea that the upper catchment of the Bentley Trench is maybe up for grabs for Thwaites to grab. And it gives us a window into these water systems, the active sort of evolution of water systems underneath Thwaites, and perhaps how that shapes its configuration. So now we're going to move a little downstream. So now we're going to look at the eastern shear margin of Thwaites. So this is the area that divides Thwaites and Pine Island. And if we look at these black lines of these shear margins that divide flow, you could imagine drawing, again, most of them. You say, okay, sure, here you go. Here is this, volcano. We've got this black line here. Ice is going to flow there. Cool. Here's some high topography here. We're going to have, a shear margin there. The ice is going to flow down there. It's going to look like some, pictures of the Alps with glaciers flowing down a valley. We got, shear margins here. Makes sense, makes sense, makes sense. And then there's the eastern shear margin, which I would never draw here. It's going to go from this, deep basin over these highlands. That's weird. You go here, goes again over this high topography. I would never assume, I would never draw it there myself, just from the topography. So then there's this question of what is controlling that location. Now, in a similar way as we've been talking about so far, you can look at the reflectivity here on the bottom, and there's a clue. Just like we were talking about before, in the fast flowing regions, you have higher reflectivity. In the slow flowing regions, you have lower reflectivity. If this would correspond to the idea that it was frozen in the frozen bedded in the slow flowing and thawed in the fast flowing, but that still gives you sort of a chicken and egg situation. Is it that because the fast flowing is thawed, that's why it's fast flowing, that's where the boundary is? Or is it just it's flowing faster, it produces more heat, and that's why you have water on the bottom? So there's still this question of like, why is that divide where it is? So this is where, our involvement in this TIME project that I mentioned before, with all the acronyms, came up. So we're looking at this shear margin specifically because it's between the two fastest changing glaciers. And this is where we've, the engineering part of my group, has really kicked in to try and give us new geophysical ways to ask questions about that shear margin. So on the left here, one of my PhD students, Nicole, was working on the idea, there's a hypothesis that the shear margin is where it is because of heating, that the shear itself produces warm, softer ice. Once that warm, softer ice is there, that maintains it. And so the question is there warm ice right in the shear margin? Now, you guys know from the earlier slides, because of that exponential plot, the warmer it is, the more it will absorb energy. So we can say, is there an absorption anomaly right there under the margin? Now, the challenge is to do that with a normal monostatic radar is hard because you just have these ambiguous pulses going along. So you could want to do a bistatic survey with that. The challenge with that is any commercial GPR can't have offsets of kilometers or 10 kilometers in order to allow you to do this, right? If you had cables, that's way too long. Cable losses would totally kill your signal. So what Nicole did is she took a software-defined radio that was initially used for consumer radars and electronic warfare and programmed it to eavesdrop on the transmitter that we had stationary here. And this would allow you to carry this receiver for larger and larger offsets and then do a tomographic study where we could resolve. And you can see if we only had 1 kilometer offset, you could kind of see a warm spot. 3 kilometers, you can see it better, and 10 kilometers, you can really resolve it. So this is a case in which one of the students built a custom synchronization radar that could let you have these large offsets and let you resolve these thermal anomalies. So that's how we're going to test that hypothesis. Another hypothesis is maybe it's the crystal fabric of the ice itself that governs why the shear margin is where it is. Tests are done in labs with different crystal orientations of the ice, and you stretch them and they have different strengths, right? And different depending on the fabric. And so there's an initial theoretical study done by one of my postdocs where he said, okay, for certain crystal orientations, you can get birefringence effects where you can get changes in the polarity. And this is beautiful. Down here is his simple analytic models of what you think that phase should look like. And the top here is data. And even without going into the details of the birefringent propagation, it's still very amazing that the data reproduces these patterns with such high fidelity. Now, this requires a polarimetric system. A lot of the data that we collected over the shear margin here was not in a polarimetric system, but it turns out that the birefringent rotation of the signal causes losses in a single polarization system. And that's annoying, and you wouldn't ever choose a system to do that. But what that produced is artifacts, loss artifacts in the radar profiles, because you're rotating. So if your antenna is in one polarization and you rotate your signal out of that polarization, you lose the energy. And it made these loss fringes over the radargram. We were able to both measure how strong the losses were and where they were in order to get this crystal fabric across the margin. So this dashed line is the center of the margin. So now we're able to see what is the crystal fabric across the margin. That gives us both a sense of what is the shape of stress across the margin and allows us to test this hypothesis, is the fabric itself governing how the margin behaves? Okay, that's our hopeful take that over our COVID delayed next field season will give you an answer for why that shear margin is where it is. Okay, now we go downstream some more. So, okay, we talked up here, Bentley Trench, we talked here about the shear margin going down. Now we have the Eastern Ice Shelf with weights. The Eastern Ice Shelf super weird also. Look, this is one of the fastest changing areas. You have lots of acceleration except for this guy, right? This blue thing here. So there's this sense of like, oh, well, maybe this piece right at the border that's slowing down, maybe that's, stuck and it's going to stabilize the ice sheet for us, right? You have this area of high topography on that the ice shelf's stuck on. So sort of a high topography on the bottom of the continental shelf sticking up, and the ice got stuck, and that's what's slowing it, buttressing it backwards. So say, okay, is that going to help us here? Now, much of our modern data, only goes back a couple of decades. And so if you want to, ask the glacier, like, how's it going? What's happening with the bottom of this ice shelf? You would need older radar sounding data. Now, we're really lucky that in the first surveys of ice penetrating radar data that was recorded on optical film, there was one flight that crossed the Eastern Ice Shelf. And then we have these 2 modern lines that are pretty close. And so what we did is we went to the Scott Polar Research Institute a couple years ago, and I brought some friends of mine who were art historians who happened to be out of work, and went and spent a couple of weeks and hand digitized with this Hollywood film scanner all of the records of these early film surveys from the Scott Polar Research Institute. I mean, it's really amazing, these radar systems recorded on optical film. And you can see here, so this is a published paper of this piece of film, and here's our digitized record. So you see much higher fidelity. You can also see that whoever was publishing this paper and put a piece of masking tape to mark their super cool feature, left it on there, and that's 50-year-old masking tape, still messing with the film after we scanned it there in black. We have much higher resolution images, And with that, we can actually compare these and see that here you go. So here's the regrounding piece. This is a piece of high topography that's slowing it down. You can see it's regrounded over that whole extent. You can see here the regrounding is much smaller. You can see here this piece of the bed, and you can see it getting thinner. And we can actually see from the bottom that even though on average what you would measure from an altimeter, it's not thinning as much because it's averaging, you can see these patterns of much higher thinning in spots. Then once those break through, that will be what takes the ice shelf out. So the ice shelf's unlikely to save us. This is also really amazing. I mean, this is modern digital radar sounding data, and this is, 1960s, 1970s radar analog technology recorded on film. It's really a testament to the quality of those radar engineers. Now, for me, this is going to be a side self-indulgent rant for a moment. That is great. The ability to see the shape change is cool. But for me, one of the really attractive things of digitizing this film was to say, could we use it radiometrically? I said in the beginning, we look at how bright the reflections are. So if we're going to try and reverse engineer these things to see a radiometric signal, here's what we're looking at. So you have these Z-scope records here. So it looks like a radargram. That's what I showed you before, recorded on the film. Now, in order for it to be recorded on the film, they had to do a lot of compression to get it to use the dynamic range of optical film, which is hard but clever. Then they had these A-scopes, which are just oscilloscope traces, right? And so you can see these red lines correspond to one of these traces. And so that's the surface, that's the bed. These things are really radiometric. They're just an oscilloscope, a picture of an oscilloscope, but they're infrequent, right? They only occur every red line, and you can have a subglacial lake that you just miss, for example. So the question is, can we combine these two? So your initial instinct may be no, because what is happening, the compression they did is they took, so this is the A-scope, so this is a compressed pulse, a log detected pulse, and then they took the derivative of that pulse and recorded that. And you can see these are two different SNR echoes, and you can see that basically all you're sampling is the side lobe structure. So if it gets bright enough, you're just seeing the side lobe structure. But if you were to measure a pulse that's weaker where there's noise, you're taking some chunk of time and you're measuring the slope where your sort of peak is sticking out, and you're measuring the slope, the derivative here. So it's mostly noise, so it's flat, and then your peak starts to push it up and you start to get a little bit of a signal. And what you can see is that actually you do, for these low SNR signals, you do get a bigger and bigger Z-scope signal. So there's a point here where your Z-scope goes and then it saturates. So sort of counterintuitively, we do have a radiometric signal in the Z-scopes, but just where the bed is weak. So if we go through and we do an experiment with this, we say, okay, here's the Z-scope, this is the film, here's the thickness from the film, here's the Z-scope, just how saturated is that echo on the bottom, here's the A-scope, and to first order, okay, those guys seem kind of similar, they seem to match, and you can use this calibration. And what you can calculate from this is you can calculate an attenuation rate in like weird Z-scope units of like saturation per kilometer. You can subtract that out. You can get peaks here. You can calibrate it using your A-scope, and you can get physical reflectivity values that make sense. And you can see that if you zoom in on these things, this is a subglacial lake. Here's the peak. They have similar reflectivity signals that you see in modern data. There's really hope here that you're able to have a very reasonable range of reflectivities, and you're able to get these spikes that correspond to subglacial lakes. So I think this is a very exciting thing that puts these Z-scopes on the table. Now, what we'd love to do is compare those signals to modern data radiometrically. Now, at this point, we're getting kind of greedy in that we have these old flight lines and we're hoping modern lines fly over it. And so we did get lucky that there was here in East Antarctica one flight of modern data and archival data that are similar. And really amazingly, so they look similar to each other. You even see some shapes of the floating piece of the ice shelf that's similar. And you see this reflectivity signal. This is reflectivity from the film. This is modern data. You can see a very similar reflectivity pattern. So we're not seeing change, but we're seeing decades apart reproduction of the radiometric signal. Now on the right here, this is a repeat of modern data where there was change. And you can see here these areas in red where you get like almost 10 dB gain in reflectivity where there's water. You get drops where you see crevassing. And we have this whole area here where you're actually seeing waters penetrating like, I guess, 15 kilometers deeper than the satellite grounding line. So My hope is with the persuasion of, hey, we see the same radiometric signal here, and when we did repeats with modern data, we saw changes. This will motivate modern surveys to refly all of these archival lines, because I really do think we can do radiometric comparisons. So this is exciting. This is the whole reason I wanted to do it. You know, this is, I hope, I don't know, you guys are on Zoom. I hope someone out there is as excited about this as I am. Okay. Cool. So that was the film piece. So we were talking here, you know, the ice shelf. Now, the next piece I want to talk about here in the big picture of the divide between Thwaites and Pine Islands. We just said, okay, the Bentley Trench, maybe Thwaites can grab it. The eastern shear margin, who knows why it's there? Maybe it's fabric, maybe it's temperature. Those are things that can change. We just said the eastern ice shelf of Thwaites, you know, is thinning, probably going to go away. Now we look here at the coast between these guys, and you see here, this is reflectivity again, this is tilted sideways, that right between here you have this dark blue area of frozen bed. Same thing happened in ice sheet modeling. This is from surface velocities. You have this area of frozen bed between the two. And so the question is, what happens if this piece of frozen bed between the two glaciers thaws? This is my student, Eliza's working on this. And she's looking at it as a big picture question as well. So if you look at the modeled basal temperatures, you have areas where the bed is very frozen. Okay, cool. Frozen enough, you could imagine it'd be hard to thaw it. You have areas where the bed's already thawed. Cool. And the question is, in these areas in between where it's frozen, but maybe not that much, what would happen if this piece of frozen bed thawed? And how would that shape the response of the ice sheet and the reorganization of the ice sheet? And so the experiment she's working on is saying, okay, she's looking here at the basal friction of areas that are frozen and saying, okay, there's a range, taking the areas here that are thawed and saying, okay, there's a range, but it's lower. So when you thaw things, I mean, it makes sense. It's easier to lubricate. And is doing experiments with, if we take these, what we're calling thawable patches and thaw them, what is the impact on mass loss? So we say, okay, what if we thawed everything that was only 1 degree below freezing? What if we thawed everything that was 2 degrees below freezing? You know, 3, 5, how does that change the amount of mass loss? And where are the areas? So you can see here, I mean, it's hard probably with the colors over Zoom. You have here is like these areas that are within 1 degree of thawing, you know, where you're getting mass loss here, areas where you have within 4 degrees. And I think, you know, this is preliminary work from a student. But I think the takeaway is starting to think through, where are the areas of the ice sheet that are maybe just barely frozen? And where are the areas that if they were frozen and thawed would have a big impact in terms of ice loss? And how can we prioritize follow-on studies where we have better processes in the modeling and better observational studies to really measure? I mean, this question of like measuring down to a couple degrees how frozen is the bed, that's a very provocative and interesting observational challenge as well. She's really putting on the table this process and asking these questions about whether that might also shape this divide, both between Thwaites and Pine Island and more generally. Okay. Now, if we move off of this boundary between and try and say, okay, what other clues do we have from elsewhere in the cryosphere, you know, in the past of the ice sheet, we can look and say, okay, we know that Pine Island and Thwaites retreated on the continental shelf across areas where there were deformable sediments and then moved across areas where there were bedrock. We know from ice sheet models that if you have bed rheologies that are more like deformable sediments or more like bedrock, it governs whether or not you get retreat over 300 years or whether you stay in the same spot. So we'd like to know whether there's bedrock or sediment underneath Thwaites and Pine Island right now. Now, one of my other students, Mickey, is working on the larger challenge of geostatistics. So, you know, we have to interpolate our data. Our data is always very sparse. So she's adapting techniques from actually basin modeling and reservoir modeling. Say, okay, can I do geostatistical interpolation? So here's an area, for example, of this map she's produced, and she's produced many geostatistically consistent realizations of this map. Here's what the current interpolation is like. And she said, okay, here's 2 realizations. They're different, but they're geostatistically consistent with the data, which is not the case here. This has allowed her to talk about where you could have water storage. You can imagine, you know, it'd be hard to put a lake here in this smooth thing that was interpolated, not hard to put a lake there or there. So that shapes ideas of where we think water would be distributed underneath the ice sheet. It also shapes routing, right? You have high topography and where you would have water flow. And you can see here, in these cases, you know, water flows here in that case, here in this case. These are all geostatistically equivalent. So Mickey was really making these tools to understand the geostatistical character of the bed. But we can also pivot those tools to ask explicitly the question, which pieces of the bed under Pine Island and Thwaites are most like these pieces of the continental shelf where we know for sure they are sediment or bedrock. And so she's done this approach she's working on now, where she said, okay, here is definite sediment bathymetry, here's definite bedrock, we train on that, and then we characterize the distribution underneath Thwaites and Pine Island. So this is her paper where we can have a spatial map of the distribution of sediments and bedrock from this geostatistical character. And then also there are complementary modeling studies where people are looking at the friction coefficient. And just to first blush right now, this is not using McKee's data yet, but you can see that the distribution of sort of low friction in parts of Thwaites corresponds a great deal well with, where her current characterization of sediments versus bedrock are. So that's a piece I think that moving forward as these converge and as we get more information from the field, this will, I think, also shape our view moving forward. All right, looking maybe further into the future, we know in Greenland that surface melt drives a lot. Now, there's not tons of surface melt in Antarctica right now, but you could imagine in a warming world that it would happen more often. The sort of mental model in Greenland is that you get these big lakes on the surface, then you find a crevasse or a moulin, they go to the bottom, you flush it like a toilet, and it lubricates the ice sheet. And so there's a question, it was hard to look at where this melt was happening and predict the dynamic response of the ice sheet. It wasn't always where there was most melt that things were accelerating most. And so one of my students worked on this problem of looking at this as a MIMO array of radar. So rather than a radar we fly overhead, these radars stay put in one spot and they record data over a year. And this is a MIMO array, so you can steer and do sort of 3D imaging with it, which is lovely. So we just looked at the power over time. So the radar's propagating through the subsurface. And one of the things that's really provocative here is over the whole winter, what you see, this loss of power. This is massive, 50 dB. This is 10 to the fifth. You can argue about lots of radar corrections, but 10 to the fifth is a giant signal. And this weakening of the signal fits these curves, which what these curves are from is saying, what if we just took all the local melt and we stored it just below the radar system? And you can see it corresponds very closely to that amount. So what this is saying is the local melt isn't flushing to the bottom like a toilet, but it's going into the subsurface of the ice sheet and staying there, in this case, at least to the winter. So that opens up this question of how is the subsurface and near surface shaping the percolation of melt down to the bottom and changing the dynamic response. Now, you guys probably saw, there's this melt season in 2012, which made the news. There was this, all of Greenland is melted, event. And what that meant was every piece of the surface of Greenland had melt conditions in that day, not the whole ice sheet had melted. Another student of mine, Riley, is looking at this and saying, okay, how did this leave a permanent mark on the ice sheet subsurface, right? Or was it just like a good news headline? So he was looking through these much higher resolution radars, and you saw, okay, here's this bright dark echo. This is the 2012 melt surface that makes some ice. You can see here in 2013, it's being buried a little, and you can see here in 2017 that ice layer has stayed. So this raised the provocative possibility that this is really reshaping the subsurface. Now, from a nerdy electromagnetic point of view, this was great because this was a case in which, in order to really model these things, it required you to do sort of the full electromagnetic simulation of many interfering layers of various density and to deal with the finite bandwidth of the system. But when that all came out, it showed two things. It showed, one, that these areas of ice that were formed by this melt season were becoming more connected, and two, they were getting denser. And this mixture of increased density and increased connectivity was reducing the permeability. And the mental model this points you towards is one of these, melt seasons. So if you think of a normal melt season where you say, okay, here's some melt and then water's going to percolate through the firn into the ice, right? And you have normal variations in that. If you get one of these severe melt seasons, you're going to get an area of ice that is no longer permeable. It's becoming thicker and more connected. And then your normal melt variations that try and deposit melt in that you want to percolate through those layers, they're impermeable now. And that water is going to stay on top of them. And then it's going to freeze and it's going to get thicker. You can have a situation where one of these or some of these extreme melt season events can permanently change the percolation and permeability profile of the ice sheet. So, okay, so that raises the possibility that changing in the surface melt can reshape the responses here. Okay, I want to briefly, as we're wrapping up, before we go to 15 minutes of questions, talk about a couple of our undergrads who have really risen to the occasion during COVID to investigate a couple other processes, and some of them may be applying to your PhD programs. So, keep your eyes open. One of our students, Annabelle, who's a geophysics major, was looking at, in the film data, questions of, are we seeing reflections from the bottom of a subglacial lake? And this requires some level of, imagination and optimism. But you see here, you've got like the lake surface, and then this reflection here that makes you think that it could be the lake bed. And in the same way, these A-scope traces, here you go, here's the lake surface, and then you get this little bump here. Is this the lake bed? And what is striking is in the old film data, it does seem to hold up. The reflections of these bottom reflectors are attenuated by the amount you would expect from sort of plausible attenuation rates of water for thicknesses that are sort of in the scale of 10 meters thick. You can see in its character that it's getting deeper and it's fading. It's not a constant reflectivity, and these calibrations I presented earlier allow us to make those comparisons. In modern data, we have reflections that look plausible, but so far they've mostly been failing to pass these tests. They're either side lobe effects or mostly that so far. So the state that Annabelle's solving here is to say, is it the case that this really is the bottom of a subglacial lake? And if so, why do we keep seeing it in the older data and not the modern data? Like, what are we worse at now than we used to be? I think one of the main things that this older data had going for it is it was collected at a lower frequency with a big cross-track array. And many of the current modern data have nice cross-track arrays, but higher frequencies. And ice is pretty accommodating to you using higher frequencies. It's pretty low attenuation across frequencies, but water is less accommodating. And so I think that may be what's happening here, is that in many of these cases, our higher frequency, higher bandwidth systems are not seen to the bottom of the lakes, but it's a provocative thing that could let us look at how, lake thicknesses are changing. An area where the modern system is totally excelling is a project that was done by one of our summer undergrads from SUNY Buffalo, John Bissett, and he's now a PhD student in mechanical engineering at MIT. But he looked at this reflection, the subsurface reflection here that was beneath a crater. So this is the Hiawatha crater in Greenland. And this paper came out. It was very exciting. Oh, it's missing the citation here. So this is not our work. Well, this is our work, but there's a separate set of papers about this crater that were very provocative, very exciting, and said, okay, hey, we think this is a crater underneath the ice sheet, and we think this is the groundwater table. And the idea that groundwater table wasn't the most exciting thing about that paper, broke my heart as a radioglaciologist, because the idea, we were just talking about Annabelle's paper about how hard it is to see through a subglacial lake. How on earth would you see through the bottom of the bedrock and see this groundwater reflector? And so what John did with his summers, he went through and he said, okay, I'm going to do forward modeling, and I'm going to say, okay, if there's ice and then some sort of drained basal layer that's not water, and then you have the water table with water and this, same rock, what would it take? Because we have two things. We have, how does the echo attenuate as it gets deeper, and how strong is the reflection? And what you get is you do get an overlap from these two constraints that are consistent with more porous bed that is drained above the water table, and then water. And so there's a couple things that are provocative there. One is, maybe the reason we haven't seen it anywhere else is because this is the bottom of a crater, and the impact broke up the bed to make it porous enough that you could drain the water out. Because if there's any water in that rock, it's hard, it's going to attenuate it, you're not going to receive the reflection. And maybe that gave you the situation where you have drained bed and then water table. The other possibility here in the bottom is that, just as I was criticizing before, our current systems, move to higher center frequencies, and that's tough for making it through water. The side lobe structure is really good. And so you can see here, this is the wideband system that was used. Your range side lobes go way down, so you can see these reflections here. Whereas in many of the previous systems, the side lobes are much closer to this reflection. And this is a very hopeful picture, because this says maybe these wideband systems could let us map groundwater elsewhere. But in this case, this paper really does seem to suggest that we are seeing the water table there, at least in this one spot beneath this crater in Greenland. The final undergrad project I'll talk about, which you can see a talk at AGU on, is Akua, who's one of our undergrad electrical engineering majors. She was looking at this same array we were talking about before. You leave this array out on the ice sheet, and it, in the previous study, I talked about it observing changes of absorption of water within the ice sheet. In this case, when we went back a year later, a crevasse had opened directly underneath the array. You can see the array hanging out over the crevasse there. Now, this was initially super exciting because when else do you get to see, radar measurements made over a whole year watch a crevasse form? And so the initial goal with this was to really look and see the appearance of the crevasse and really understand some crevasse processes. But Akua actually went through this sort of whole year of removing artifacts, because actually sort of torturing a radar like this produces tons of artifacts. Your array has shifted over the course of the year. There's RF interference, there's airplanes flying overhead, there's military bases not far away. And she's done this incredible work of removing all of these artifacts, which will be a freestanding paper on its own. So if you're really into removing radar artifacts from a MIMO FMCW array, have we got the paper for you? But after you do all of that, what's amazing is it does look like we have signals here of a reflection from the bottom of a crevasse in our time series. And so the follow-on work she's going to do is actually look at that formation and see what insights that produces for crevasse formation and perhaps also the physics of fracture and calving. And with that, I'll stop, and thank you guys for sitting and staring at your computers and listening to me.
All right, great. Thank you, Dusty, for your wonderful talk. And now it's time for questions from the audience. And before you speak, please remember to unmute yourself so that we can hear you. Or you can simply raise your hands in the chat. I can see people clapping. Well, I guess I will ask the first one before when people are still formulating theirs. So as a seismologist, I'm wondering if you see any ways that seismic measurement could complement the radar measurements on the subbasal features.
Yeah, I mean, I think definitely. I think, for example, these questions of trying to see through a subglacial lake. I think that there's, the seismic data would make it through the lake easily. Now, it may not put strong constraints on the thickness depending on the wavelengths, but it would at least let you know that it's there. And if you could get a thickness from the seismic data and you could get these echoes, one, it would confirm, hey, these echoes are in the right spot. And two, if you could calibrate those echoes, then you could start to constrain the attenuation in the lake. And from that, that's going to give you an electrical conductivity, and that can give you, ideas around sort of salinity. So I think there's super powerful combinations there. Also, if you imagine, things that are going to affect, if you wanted to quantitatively look at the reflectivity of the seismic data, that's going to be responsive to sort of the geometry of the subsurface. And since the seismic waves are much longer wavelength, it's pretty straightforward for a radar to go through and see and resolve that finer scale geometry and correct and remove that term. So I do think if you're, if you view the radar as sort of giving you a lot of information right at that interface, and the seismic giving you lower resolution information deeper, I think there's profound potential in the synthesis.
Great, that makes sense. Other questions?
This is Jeff. Great talk, fantastic. Yeah, it's really, really exciting. So if you were asking whether there was one person out there who was really excited, yeah, I'm excited.
That's great, that's nice.
Well done. Yeah, so my question is kind of a little bit off topic, but I was just amazed to see the quality of that old data, and I didn't know about that. And I should probably, talk with you offline sometime about how you go about doing that, because you may know we're looking for old ice, and you may actually be involved in our program too. I'm not sure. Some of your mentors are involved.
Yeah.
Yeah, so we're trying to look at a pretty sparsely surveyed part of East Antarctica between South Pole and Dome A. And then I noticed on your line map, there's a lot of that old data there. So I got really excited about that. So anyway.
Yeah, no, absolutely. And we're working on, so as part of that project, the Stanford libraries, which are a persistent public repository, have hosted all of the data. And so if so all of the films are there in perpetuity, anyone can use them. It takes a great deal of zeal to go through millions of film photographs, but we're working on some tools that will make them much more usable. And if any of you or anyone who's listening wants to, dig through it, we can help you use our sort of beta level tool. The real adventure comes in for some of those lines, where we don't have positioning data. Some of it's just been lost sort of archaeologically. But that leads to sort of fun puzzling where you can look at, photographs of the original flight plans, where they were flying from, and then you can kind of try and extrapolate it. So depending on the exact line, there's different levels of fun required. But yeah, I'd love to talk about
it. Data archaeology.
Yeah, totally.
Yeah. No, that's great. Thank you.
Thanks. Other questions?
I have a question.
Yes, please.
Hi. Yeah, fantastic talk, Dusty. Wow, really enjoyed that. Just following on Jeff's question, I love this idea of reflying some of those older radar lines. So I was just curious, kind of, is that something you would start in West? Do you have a favorite area you would start with, and you have a dream team of radar instruments and frequency ranges in mind, and things like that?
Yeah, I mean, so it is still fresh enough to be amazing to me that the modern reflectivity pattern over that East Antarctic ice shelf matched what we could get from the film. Even at my most optimistic, I didn't really dare to hope for that. And so, I think probably we would look for areas where that is the case, where we have nice, clean radiometric signals. Now, if you want to look for radiometric change, I mean, things that you could expect to change over 50 years, I think grounding lines and ice shelves are good ones. They change quickly. I think areas where you have lakes, especially active lakes, I think that's another area where you expect to see this. An area I'm super excited about is last summer, we went to Copenhagen and also digitized the whole DTU archive of Greenland data. And I think, in Greenland, we have these fern aquifers that evolve, and we're working with Nina Carlson and Winnie Chu on getting some analysis of that out. But, if this approach holds, the idea to look and say, well, what was the state of fern aquifers in the 60s and 70s, I think is super provocative and exciting. I think, in Antarctica, I would just go through and do we can help do a quality check all along, I suspect East Antarctica, and anywhere where there's nice clean grounding line signals, and then bang on reflights. The data was collected in many places with both 60 megahertz and 300 megahertz data. So spanning those, or at least getting systems that could allow you to extrapolate to those, that's nice. The signals aren't so different, so you'd be all right if you just picked one of those. That helps you as well. I mean, what's heartbreaking to me is the lines that we used in the first paper over Thwaites has two frequencies, 60 and 300 megahertz, great lines over the eastern ice shelf and the grounding line, but it's one of the only pieces of the record that we don't currently have the A-scopes to calibrate it. So that's personally heartbreaking, but maybe somewhere in the remaining millions of images is the A-scope data, and some enterprising, undergrad with machine learning algorithms will find it for me so we can use it. But yeah, if you ever have an airplane at your disposal and want to fly these lines, we will help you plan those flights for sure.
Thank you.
Right, nice. Any more questions? Well, if not, we will just wrap up here. Let's thank Dusty again for his wonderful talk. Thank you, Dusty.
Thank you for having me.
And next month and next week, we'll have Sabine Stanley from Johns Hopkins University, who will talk about geomagnetism and related stuff. And I hope that everybody will stay tuned for that. And thanks everybody. Bye.
Thank you.